Okay, so now we're going to talk about moments, all right? And a moment is the tendency of a force to produce a rotation. So this is like if if this force P pushes on the midpoint, it's just going to move the object forward. That's called translation, okay? However, if it pushes on the arm here, all right, it is going to cause it to both translate, move forward, and rotate around, all right? And here, if we look, if it were pinned at this point and we pushed with force P, you're not really going to get any translation, it's pinned, but it is going to rotate around like this, okay? So, that's what we call a moment. It's a tendency to cause a rotation. Right? The moment arm is the perpendicular distance from the line of application to the point of rotation. All right. This, in this picture, this is the line of application. This is the point of rotation. All right? So this distance D is the perpendicular distance. If this hand were here instead, okay, all right, you might try to say, well, this is the distance, okay, but that's not the distance because that's not perpendicular. So you have to do perpendicular from this line going through the point of rotation. Right? And so the distance would still be the same, D. Okay? We have to pretend how far do we have to move in just one direction, okay? It could be X or Y, all right, to get it in the line of action, all right? Okay, so a moment is calculated as a force times a distance, all right? That means it's going to have units of force times distance. Remember that anything we do to numbers, we're doing it to their units as well. So it might be something like pound inches, pound foot, kip inch, kip foot, Newton meter, okay? Now, um, some of you may have already thought of something else that has units of, sometimes we say foot pounds, and that's torque, all right? Because torque and moments are the same thing, a tendency to produce a rotation, okay? Now, we have a convention about whether we're calling it positive or negative, all right? A clockwise moment, okay, going this way, is negative, all right? A counterclockwise moment, if it tends to rotate in this direction, we say that is a positive moment, all right? So let's look at this, all right? Here is our center of rotation. Here's where we're applying our force in this line of action. So we draw the perpendicular distance between those two, and it's going to rotate. Now imagine that if this is you sitting in a rolly chair, and you have your arms out, okay, and I push here, this is your hand, okay, which way are you going to rotate if I'm pushing right here? You're going to rotate this way, right? Okay, so when you are going to rotate around that way, that is clockwise, right? So that is going to be a negative moment. All right, on this one, imagine this is like a lazy Susan on your table. Okay, so all your stuff's all over your little lazy Susan, and that's the center where it rotates about. If you push here on this edge, okay, because you're sitting back here in the chair, okay, you reach over here and you push this way, which way is that going to rotate? It's going to rotate this way. all right, and that is a positive moment, all right? Okay, so let's do this problem, all right? We want to know the moment, all right, caused by these three forces on, with O being the center of the rotation, okay? So we've got to deal with F1, F2, and F3, all right? Now, F1 is in the same line of action as point O. It actually, remember that we can pretend that forces are applied anywhere along that line directly that they're in, okay? And so there is no moment around O due to F1. You can think of it this way. If there are moments, okay, due to things, they're going to rotate. So just pretend instead that F1 were right here by itself and it's pulling this way, okay? Is that object going to rotate or is it going to translate, or both, okay? And I think you can see when you think about it that way, if you were pulling just like that from F1, that there's no moment, there's no rotation due to F1, okay? So let's make a note of that. Oh, I did that wrong. Okay. Alright, so then let's look at F2. Alright. F2 um, is all in the y direction. Okay, that's no problem. And it is 5 feet away. Alright, so we said that M1 was 0. Alright, so M2 is equal to F2 times D2. Okay, and that is going to be equal to 75 pounds times 5 feet. Get that right there. Alright, so then when I'm here, and I'll go ahead and calculate that. Alright, let's see, let me get my calculator out. Tools. Alright, let's do this. Okay, it's going to be 75 times 5 is equal to 375. Alright, so that becomes 375 pound-feet. Okay? Alright, now, here's the other piece of this. Alright? We need to now, okay, find the moment due to F3. Alright? But if we look here, it is hard to consider this with this at this angle. So another way to look at it would be like this. Okay? If we have this force, okay, F3, it's actually made up of two components, F3x and F3y, okay? Alright, now, so Oops, I didn't make it quite long enough to. Alright, so if this one is F3y, alright, oh, that's x, sorry. Okay, and this one is F3y. Alright, what do we know? F3x is passing directly through the point O. Alright, so there's not going to be any moment due to the x component of force 3. There is going to be a moment due to the y component. Alright, so I'm going to try to grab that. No, it won't go away for me. Alright, and so the distance from this point to this point is going to be the same as the distance there. Alright, and we'll use the same formula. Let's look for a moment. We forgot to talk explicitly about the sign on the moment of 2. If you only consider force 2 acting on point O, if you're pushing here, and it's going to rotate around O here, okay, push here, then you're going to tend to have a counterclockwise rotation, and we said that was positive. Alright, so we do have the sign right for moment 2. So now let's go back and do moment 3. Okay, and moment 3 is going to be F, it's going to be 3y times alright, and that's going to be equal to F three sine of 30. Let's just go ahead and plug in the number for F3 too. It's 60 pounds. And all of this times D. Okay? Let's see what's happening here. There we go. Okay. And that D is the 5 feet again, alright? Because the distance from here to here is 5 feet, the moment of rotation. Alright, so let's get out my calculator and see what we've got. Well, shoot, I don't have a calculator. Hold on, I'm going to have to pull up one that has scientific function on it. Alright, my handy dandy calculator. I prefer to use my regular calculator at the office. Let's do, alright, we're in degrees, so 30 sine half times 60 times 5 equals 150. Okay. So we have 150 pound foot. Alright. Now this, okay, moment, if we're looking at a force pulling down here, rotating around O, we're going to tend to have a moment going this way. Alright, it's going clockwise. We said that was negative, so let's not forget to have our signs correct. Okay, negative, negative, negative. Alright, so the moment is just going to be M1 plus M2 plus M3. Oops, 3. Okay, so M is going to be equal to 0 plus 375 plus a negative 150. Okay, so M is equal to, let's see, on a good day, 375 minus 150 will be 225, right? 2. Alright, and the units on that are pound foot. Lots of times when we write units multiplied together, we put a dash in between them, so don't think that's anything special. It just means it's a pound times a foot. Alright, so now it's time to work some of the moment problems in your homework. So you see that on your weekly things to do.